Odom, and thank you for coming. It seems like the small number of us, you don't have to do chat. You can speak up and ask questions. We can go pretty interactive. Just talk a little bit about our agenda here. So who is this for? Our motivation, definitions of basically what we're describing, how we describe performance. And then this course is actually designed to be a hands-on lab. We have 7 modules to go through. So this is going to be kind of like a preview of something that we hope to publish here in the next couple weeks. So look for that to be available on the Intel Devcloud and potentially on JLSE natively. There is a bit of a setup process that to get Jupyter Lab running on JLSE that we've documented. So who is this for? This presentation is for developers who work in heterogeneous environments. We're hoping you are familiar with data parallel C++ and that you have some experience with roofline analysis in Vtune. If you've not had a chance to take a look at data parallel C++, please take a peek at Learn the Essentials of Data Parallel C++. It's featured on the Intel Devcloud. You don't need anything but a browser to get started. All of the software is up there, and you should be able to get going within a few minutes. It's a great opportunity. So what's the motivation for this course? So every day it seems like we're reading about new custom hardware that is supposed to, provide some acceleration, some feature, do something better. Coming out every day. And then, in addition to that, you have our traditional x86 CPUs with multiple generations and different instruction sets. And of course, you throw in FPGAs and ASICs. And you get quite a vast number of different accelerator targets to hope to take advantage of and maximize your performance while not writing a ton of code. So, the goal of this whole course is to show how to develop performant and portable code across a diverse set of platforms and, make it perform as well as possible. We are going to use our Intel's oneAPI and data parallel C++ to demonstrate how to do this. And we're going to show portable performant code across several different platforms available on the Intel Devcloud and JLSE. And so those are basically Xeons, Gen 9 GPUs, and NTG1s. So just some definitions. And this is kind of important because we're going to define performance as a measurable quantity representing a characteristic of an application run on a platform. And this is, throughput or time to solution. And it's also, we really look at it, and we'll show you guys later, as a percentage of peak performance. We can take a look at this in the notebooks. And that's really what we show is as we evolve an algorithm, how to maximize the performance across all of the platforms while trying to minimize the amount of code that happens. Portability, the ability of application to run correctly on different platforms. Correctness is key, and the ability to run the same code on multiple platforms is key. So actually with data parallel C++, our code divergence is really 1 because the code runs correctly without any modifications across all of the platform. And then of course productivity, and this is the ratio of application code that you needed to implement to get the features or the optimizations, etc. Out of scope for this, though, is benchmarking, competitive analysis, or a critique of any particular type of hardware. And the reason for that is, benchmarking is extremely difficult. oneAPI is evolving rapidly. Compiler changes, library changes. The hardware on the Devcloud's a sandbox, and I think JLSE is a bit of a sandbox right now with constant upgrades happening. So it's difficult to really show. I mean, we've seen improvements throughout the months that we've been developing this, just via software and that type of thing. So this is to give you an idea of how to go about achieving performance, portability, and productivity. Any questions? No? Okay. So this our mantra here is an application's performance portal that achieves a consistent ratio of the actual time to solution to each either the best known or the theoretical best time to solution on each platform with minimal platform specific code required. So you'll see that we've really tried to embody that mantra. So at this point, I'm going to switch over to our Devcloud, and we're actually going to walk through this live using Jupyter Notebook. And this is, if any of you are not familiar with Jupyter Notebook, it's a REPL enabling kind of like just-in-time runtime, but we actually use a feature called magic cells that allow us to shell out in the background and run C++ code or data parallel C++ code. So in this first objective, we chose to use a gem for our example algorithm. This initial part here, like I said, this is designed to be a multi-hour hands-on course. So a lot of this is going to be kind of whizzing through the notebooks. I hope you guys can read it. I hope it's big enough. I can zoom a little bigger, but it makes scrolling hard a little bit. So this is designed to be a self-taught, walk yourself through. We give an introduction to the data parallel C++ programming language, talk about the challenges again. Just in case you guys, I assume everyone's familiar with data parallel C++, so I'll skip that section. But talk a little about the programming model, the memory model. And so in this very first case, we kind of showcase the benchmark, and that's OneMKL. And OneMKL is a vendor library, and the thing is, if you have a vendor library available to you and it can function for your need, it's a great place to start. In this case, I don't know if you guys are familiar with OneMKL. It does linear algebra, BLAS, fast Fourier transforms, RNGs, and of course gems. So in our case, we're going to use a two-dimensional gem. A equals B times C. And the amazing thing about OneMKL is it's really its productivity, and the entire algorithm is contained in these two lines. I think we actually ended up writing 4 lines of code to optimize our basic gem. And so what you see here is we broke our common code up into 2 different sections, and I'll go over that next in the basic one. And then we put the code that is actually changing as the algorithm evolves in the not common code. So in this case, you can see there's a bunch of setup code in our common code here, but then here we are, namespace sickle for data parallel C++. And then pretty much here's the matrix operation. We create the buffers for the matrix. And this is all for OneMKL to specify the types, and then to use the OneMKL matrices. And then, we actually execute the device to run on the library. So it's a pretty small amount of code that does a lot of work. And so on the Devcloud, you can pick your offload device, whatever that might be. And in this case, we'll choose Gen 9 graphics. And we've got a lot of scripts here that run. It's pretty awesome, though. You can choose IrisXE Max, 3 types of Xeons, and then execute the code, the gem operation at a particular size. And so in this case, we can try like an 8153 Xeon, for instance. Run the output, and this submits the job to the Devcloud. And this is very much like JLSE. We're using QSub and just kind of automating it a little bit. It's kind of the benefit of using Jupyter for your showcase environment. So it takes a second here because you are running through a queue. While we're waiting, anyone have any questions? Is everyone familiar with Jupyter?
Yeah. So Hans is asking if they can get access to the notebook.
Yeah, in a week or so, we will have these published. Hopefully up on JLSE. I'm working with some people there, to make it available to you guys locally. But it will also be up on the Intel Devcloud. So that's the plan. So as you can see, it shows a P630, a matrix size of 5,120 by 5,120, and did it in about 3 seconds of execution time. And you can just wrap around and around and see how that works for each target there. So how did it do? And this is the roofline report, and we'll go into a little bit more about this later. But just quickly to take a look at the roofline report. What you can see with oops. So zoomed, it's really hard to control. We did measurements across various sizes on this is on Iris Xe Max or DG1 across a 1,000, 5,000, 10,000, and 20,000 matrix. And you can see how it's doing. It's actually OneMKL is doing pretty awesome. If you look at a big matrix, it's basically above the roofline on multiple things. It's right at the roofline for the memory operations. It's super close for GTI intensity, efficiency here, and you're seeing a lot of green dots. And of course, it's just crushing it in performance. So what if so that gives you an idea how you're doing on roofline, and we use this tool throughout the entire set of exercises to across various sizes of matrices to give an idea how performance is going. And what you'll see is there's definitely overhead associated with setting up matrix operations, and the efficiency does go down a bit on the smaller operations, but for the most part OneMKL is crushing it. And you can go through and look at and see all of these different items, and that's what we would expect. We would expect a highly optimized vendor library to do this. Another area where we looked at was Vtune, and this is where you can kind of get an idea of how it does across various platforms. And so you can see, like on a Gen 9 with a very small matrix, there's a lot of idle time. But if you go back over here to like DG1, you can see that a lot of time is spent, with L3 bandwidth being bound. Occupancy is pretty high, which is good, but there's definitely some issues that could be better, quite honestly. So, and you can see them change as the various array sizes change on a compute-bound application. So, it can give you some idea to poke around and see what you can do to your operation. So, the rest of this basically starts with us looking at a basic gem. Let's assume that OneMKL isn't perfect for you. You have something custom or you're wanting to do. So how would you start thinking of like a library writer? Like what would you do to start developing your code or optimizing your code to take advantage of hopefully oneAPI and data parallel C++ and get close to achieving OneMKL or even possibly beating it for the most part. So in this next section, we introduce a basic gem, and we start to show how to improve the software architecture to minimize code changes, and we'll talk a little bit more about how to interpret the roofline and Vtune results as a method to measure the gem application. So I'll give you guys a quick peek. Our full code here, you guys can see is namespace. We set the initial size array to 1,000, so if you do execute it, it goes really fast. Basically setup code, describing our work group size, the matrix size. We allow you to, via the command line, programmatically tell it what size of work group and matrix to do. We initialize the vectors for the matrices. We initialize the values initially. We query the platform for the profiling. We create the matrix, and then in this case, this is our parallel 4 matrix, as naive as we can get it. No fancy stuff here. Just go for that, and then of course the timing code in the end. And so that's where you'll see the matrix kind of in its entirety. And I showed you the OneMKL version where the majority of the setup code is in another file, and we really just focus on the differences that need to happen. So this is the only time you'll see the full matrix. So kind of already talked about choosing a device and running. And in this case, we did a P630 graphics, and it ran a little slower, and that's because if you recall, it was about 3 seconds with OneMKL, and this one it's about 18 seconds of kernel time and 19 seconds of compute duration. And that's just showing optimizations that MKL automatically did. Let's see if we can actually get a DG1 node to run. I'll see what happens. They're usually pretty busy. Wait here a second. So you can see that it's executing because of the little asterisk over here. Oh, got it. Nice. Oh, check it out, Rocksheath. It's always going to P630. I wonder if the DG nodes are too busy. Well, same result. Not happening like it's supposed to. So I suspect the GPUs are too busy to get access to them. So this is kind of the code simplification. Basically, to look at the naive implementation here, these are the only 2 sections that you're really changing, right? The namespace, set up the matrix, get the command group handler and create the accessors, and then just do our parallel 4 right here. We don't do any of the like verification. We leave that off because verification is pretty slow because we do it not parallel but linear to assure accuracy. So something we talk about is roofline, and feel free to ask questions about roofline, but we use a tool called Intel Advisor to generate roofline reports. I got integrated with that, and Advisor is in a beta status, so if you have a system with, say, multiple GPUs, you might get some oddities. We're still working on trying to pin affinity down and being able to measure kernels with respect to that. But there's basically 3 steps, and the nice thing about this is if you have Advisor on your local machine, you can run this collection remotely and then kind of explore it locally on your desktop. And we can take a peek at that with Vtune later if we have time. But we run a collection, and we static instructions, tell it where to write it. We do a trip count and flop analysis, and then we generate a roofline report exporting the details to HTML. So I think you guys watched me you can configure the display levels, you can see the cache aware roofline model, the L3, the shared local memory, and then like the GTI bandwidth, that's like the memory between your core and uncore, between and what you have going on there. The rooflines are here, and you ideally want to be at them or above them if possible. And when you're below them, it can kind of show you the bottlenecks. And it sometimes suggests optimization next steps, but for the most part, I think it just gives you an idea, like, why is that way? So in this basic one, let's take a peek at this. You'll notice that there's no shared local memory. You're just seeing an arithmetic intensity here of 12.89, L3 at 12.8, and then your GTI, which is low. You could be taking more advantage of that pushed up here. So as we would expect, there's a lot we can do to improve this, and we're seeing pretty consistent performance across the different um, sizes of algorithms, right? We're seeing some speed up, because of overhead, but for the most part, um, it's taking some time. So like in the case of this 10,000 by 10,000 matrix, a Gen 9 took what, almost 3 minutes to compute the matrix. So definitely room for improvement. Uh, I think we pretty much already talked about that. So as we looked at before, Vtune, a way to do this is to collect GPU hotspots and take a peek at it remotely. We look for hotspots, memory consumption, memory access, and threading. And then we're reporting basically the summary report. Vtune is another tool that allows you to download the results directory, and then you can explore locally. And if we have time, we can take a peek at that later. But in the case of the basic one, we can see that, on a really small array, it's worked pretty good, went pretty fast. But as you go to these larger ones, you can see that time really slows down. Floating point utilization is pretty low. You don't see a lot of occupancy. And then DG1 on the smaller arrays. You see a lot of issues with small just because the overhead of the setup is taking so long. And then as you go further, you start to see some good occupancy usage, and L3 bandwidth isn't tapped out yet, so it can go faster, things like that. And I see I left ATS in here, and I wasn't supposed to. Oops, I missed one. And then the 10,000 one, you can see that it's pretty much maxing it out, and working pretty quickly actually. So in the notebooks, we talk about which one of these things you could do. And so, when L3 bandwidth is high, you want to consider improving cache reuse. Having stalled EUs is never a good thing. So you want to figure out why it's high, and because it tends to impact compute-bound applications. Floating point utilization, 100% is good, but if the value is low, it means you're probably not vectorizing very well. Occupancy is something you want to take a peek at. You want occupancy as high as possible because low values are inefficient work scheduling. So Vtune's an awesome tool, and there's a ton of resources on software.intel.com to take a peek at, and we gave a link to these down here that we'll be willing to share later. So I've been talking for a bit. Have there been any questions, Rakshit?
None so far.
Okay, so I'm going to turn it over to Rakshit to talk about the next step in algorithm improvements.
So Ben, there was actually a question about the course, and Fred was asking when you referring to the course, what do you mean? I responded that I think you guys are developing a course, but if you want to explain more, please go ahead.
Sure. Rakshit, share your screen so that we can show them the notebook. So this is actually our course. We're going to call it Performance and Portability, and it's 7 modules that you walk through, all in data parallel C++, designed to give you kind of the insight and thought that a library writer might go through. How do I build my algorithm, extending its capabilities to work better and better? And Rakshit's going to talk about the next set of algorithm improvements that we walk through, ND range, local memory. We'll talk a little bit about code parameterization, and then in the end we show a little bit more about a Vtune analysis with deep dive. I'm not sure we're going to make it to that today, but we would love to offer a hands-on course of this almost as a dry run whenever you guys are ready, and we could make this available on JLSE. We could do it on the Intel Devcloud. No problem whatsoever. You guys are totally welcome to do that. Yeah. Does that answer the question, Yasi? So Rakshi, take it away.
Okay, all right. So now, in the previous example, we just looked at the basic gem operation. All it's doing is, just doing simple matrix multiplication using this for loop here. And let's look at some more optimization you can do. This is mainly using, instead of using just a range in your parallel for, we start using ND range implementation. So what ND range mainly does is it helps you to group executions, and then each group actually runs on a subslice in the graphics hardware. So what that looks like is, if you look at the graphics architecture, it is made up of a bunch of subslice, or sometimes it's called compute units. And each of these groups has its own local memory and can execute work group independently. So mainly we are grouping execution so that a bunch of these groups can be executed simultaneously. So that's what we are doing in this example. This document mainly explains what is ND range kernels in SYCL, and we have an example. So this is mainly the code for the kernel that we have, and you can see that the main difference here is, instead of using just a range, we actually use an ND range where we specify the global size and workgroup size. And you can see that we specify the global size as n by n, and then workgroup size as m by m. And these m value is can either be specified using command line, or it can be dynamically generated based on the hardware information. Right. And mainly using this implementation, we can get slightly better performance because a bunch of these work groups are executing simultaneously. So let's go ahead and then run this. Again, we execute this. This should take about 30 seconds. So to quickly compare the results, let me go back to the previous results here. So we can see that we did 5000 by 5000 matrix, and then we had execution time of about 18 seconds. So let's look at what output we can get here. So here you can see that we slightly improved the performance. It's about taking about 13 seconds by making use of ND range kernels. Right? And then we can also look at the roofline reports here. We have for different matrix sizes. So we'll compare that with the next implementation. So we also have another implementation where we do matrix multiplication with ND range, but also making use of some private memory to store the intermediate results. So let's look at this example here. So the main difference here is it's exactly same as the previous example, that we are using an ND range kernel where we specify global and workgroup size. But the main difference here is the actual intermediate result that is calculated within the for loop is actually stored in a temporary variable here. So this will, in the hardware, this will be stored in a register, and then finally, once all the temporary result is computed, when we have to finally write it to the global memory, then we actually copy that intermediate result into global memory. So in the previous example, let me scroll up and then show you the code there. So in every loop, it used to actually access the global memory. So that's the main difference between the two code improvements here. So let's quickly run this as well. And this should take another 20 seconds or so. And we should see like a slight improvement in performance, and we can also look at the memory bandwidth between the two. So let's wait a few more seconds for the results. we can compare the results. So in the previous example, it looks like the actual execution time was about 13.3 seconds. Let's wait for the result here. And here you can see that we just got the output, and you can see that there's a slight improvement just by making use of a private variable within the kernel code. So this is taking about 12.8 seconds. And similarly, we have roofline reports generated. So let's analyze the roofline reports, right? So if we go in and then enable all the different parameters, you can see that we have if you click on these red dots, you can actually see the various characteristics. You can see that the memory bandwidth here is about 1,000 gigabytes. So if you compare it to the one where we are not really using global memory, private memory, so you can see that the bandwidth here is about 1600, right? So you can see that the main difference is there's not as much global memory access. So that's the main difference between the two improvements that we just looked at. The one using private memory will use less global memory accesses. So that's how we can get slightly better performance. And again, for this too, we have a detailed Vtune reports, which also give you, the L3 bandwidth utilization and a bunch of other characteristics, but based on the size of the matrix that is used. So that's about using ND range optimizations. So there's also a way we can use local memory. So that's in the local memory module here, which mainly talks about how we can use local memory to improve performance. So mainly instead of directly accessing the data from global memory, we would first load the part of the memory into the local memory, and then local memory is what is used to do the matrix multiplication for each work group. So the code, the main kernel code, is right here. And you can see that the initialization is still the same. We create buffers for A, B, and C, and accessors for A, B, and C, and we specify the global size and the workgroup size. Again, this comes from either command line parameter, or if you don't specify, it will use one of the default, or it will compute what is the best optimal workgroup size to use based on the device information we have. The main difference here is that you can see that we create two tiles, A tile and B tile. So this is where it's mapping it to local memory on the GPU or CPU. And we specify the size as M by M. So for each work group, there's a smaller tile of memory created, and that tile is what we are actually using to do matrix multiplication, and we, in the same way, we save the intermediate result into a temporary variable and then finally write it into global memory. So the main difference here is that every time there is actual multiplication done, it's not actually using the global memory. So let me quickly switch over to the ND range version of this one. You can see that in this code example. So every time we do a multiplication, we are actually calling it from the actual A matrix, which is in the global memory. But whereas here, for every multiplication that is done, it's accessing the local memory. So that's how there should be less latency, and you should see much improved performance, right? So let's run this code example. So again, this should take about 20 to 30 seconds. And again, in summary, so instead of accessing this smaller matrix from global memory, each time it's actually accessing from the local memory. So that's how we should see some better performance. So we saw in the previous example, we saw it took about 12.8 seconds. So using local memory, so looks like this is just completed, and you can see that it's actually taking about 9 seconds here. Much better performance, so 12 seconds to 8 seconds. So we're able to get slightly faster performance by using local memory here. So again, you can look at the roofline reports. In this case, we are actually using the shared local memory, so we should see another dot here. In the previous one, we didn't see any local memory characteristics, so you can actually click on it and then see how much memory is being used. You can see that about 1100 gigabytes of memory is transferred when using global memory. And we also have Vtune data for the local memory as well, for all the different matrix sizes, and also for when using different GPU hardware as well. So you can see that if you want to quickly compare what's the performance when using Gen 9 with 5000 matrix versus when using DG1, you can see with DG1 it takes about 4 seconds or like 2.7 seconds on the GPU time, whereas when using Gen 9 you can see that it takes 12 seconds or 10 seconds actual GPU time. So that's using local memory, right? So there's various optimizations you can do, either using local memory or using just ND range and private memory, or if there is a library available like OneMKL, you can make use of that. So that's the best way to increase your productivity. Next, let's also look at the code in detail, the kind of code parameterization we are doing. So mainly when we do have to calculate the optimal workgroup size, we do some device queries. One of the important things is, mainly to figure out where the code is actually run, we actually query for the device name and print it out, and we also print out the maximum workgroup size that the particular device supports. So this is just showing the various different hardware. So in case of Gen 9, the max workgroup size is 256. In case of DG1, it's 512, and when you're using CPUs, it's 8192 size. And we also have the preferred workgroup multiplier size, right? So based on this information, you can actually compute optimal workgroup size. So in case of the Gen 9, we could use 16 by 16 because the 16 by 16 is 256. That's still within the limit, and then that works perfectly fine. And same thing with DG1. You can actually go higher up. You can probably use 20 by 20, which falls within 512, but then it's not really a good value to have 20 by 20 since it does not divide by 8. You may not get better performance. So those are all the different options you can actually try. So we've actually written a small algorithm which actually tries to find out all the different possible workgroup sizes that can be used for any given hardware. So mainly it tries to find out whether it equally divides by the total matrix size and also is within the max workgroup size for the particular hardware. And if you use this version, you actually when you compute the value, it actually tells you, okay, this is the matrix size we have. So the valid workgroup sizes are all these, right? So you can use 80 by 80 or 64 by 64, 40 by 40, but then it picks the most optimal one based on this algorithm and uses that particular value to actually compute the matrix multiplication. So here in this example, it's the same again, local memory operation. So this will, if you run this example, this will actually, you will see that it will use this algorithm to actually find the most optimal workgroup size, and you'll see performance results based on that. So again, here's an example that is actually showing all the results using various workgroup sizes. You can see that when we, of course, the graphics is actually limited. We only have results for 8 by 8 and 16 by 16. That's mainly because the maximum workgroup size is 256 or 512. So the best workgroup size you can actually have for, in case of GPU, is 16 by 16. But whereas for a CPU, you can actually try 32 by 32 and also by 64 by 64, which gives you the best result. And here you can see that it's just showing all the different workgroup sizes that you can actually use, and then the optimal workgroup size is 16 by 16. That gives you the performance numbers. And same thing, here's an example that's actually showing for a 20K by 20K matrix size, again, on various different hardware. You can see that performance difference based on the hardware as well here. So Ben, were there any questions based on these three modules?
There was one question. How is ND range slice implemented? Does it gather across strided data into each EU's cache copy? And I think you showed the GPU memory hierarchy there. Yeah, that one. There you go.
Yeah, so mainly, so each of these subslices, you can see that it has its own shared local memory, right? So which is about 64K for Gen hardware. And the way ND range kernels work is that each workgroup will execute within each one of these subslices, and but you can have multiple workgroups that also execute on the same subslice. The main difference is that since there are multiple subslices, multiple of these workgroups can be executed at the same time. So to make sure that there is no data dependency. If there is data dependency, you do have to use some barriers in the code so that it synchronizes the data between each workgroup. What else was the question regarding something about EUs?
Yeah, does it gather across strided data into each EU's cache copy? So I think you answered that by saying it can't have. It would slow you down if you did that, right? Because you need to set up the synchronization with barriers, I believe.
Yeah.
So, yeah. So
so there's a
independent.
Yeah. So these modules, I mean, it has more in-depth, details into how it maps to the hardware and how the groupings actually work. So I think once we make this modules public, you will be able to go through this document and execute the code and then play around with different values and then see what results you get.
Yeah, we're cramming 3 hours of work into 45 minutes here, so it's all right. Yeah. So Yasi, I see we're at 9:48. Do we have a little more time, or do we need to wrap it up at 9:50?
No, you can go the full hour. That's fine.
Okay. So Ben, do you want to do the Vtune analysis?
Yeah. So yeah, sure, we could do that. Do you want to show them the analysis one just real quick so they can take a peek at everything. Oops. Uh-oh.
Okay.
This is the kernel execution time one. So we kind of put it all together here, and the one that I really wanted to show was the relative to MKL performance that we're able to achieve. And so MKL is normalized to 1. Oh,
This one?
past it. No, the one with the big, that one right there. So this is how we did. Can you zoom a little bit, Rakshi? Is that possible? So this is how we did across, and I didn't put Gen 9 here simply because it blows the scales out of the water. It's just a little too slow for this big matrix, 20,480 by 20,480. But if you look at MKL here, it's normalized to 1, and this is the relative performance. And the last algorithm that Rakshi showed was the local memory implementation. The green ones are subgroup with local memory. You can see it got very close, but you definitely can see that you can chase a library as you keep evolving your algorithm with data parallel C++. I just wanted to give this kind of overview of how we ultimately did using parameterization and scaling the workgroup size up. We were able to maximize the CPU's results, and of course using the local memory implementation, we're able to really maximize the performance. Now the 8153 does have a ton of cores in it, right? I think it has 64 cores, so pretty fast machine. So let's take a look at the Vtune section. This is something that we get asked about all the time. I think, do I just share? Is that what I do?
Yeah, you can share. I can stop sharing.
Okay, if I do blue, oh no, I screwed that up. Share this screen. Did that work?
Yeah, I can see it.
Okay. So one of the really cool things about using Jupyter as your dev environment, did I lose my dev environment? I did. Is when you're doing collection, you can actually create a directory, and then you can right mouse click on something and download it, just like boom, just like that. And so when you do the Vtune analysis and you run the collection, which was in the intro, sorry. No, it's not. It's Vtune. Here. And you emit all of this data here by running Vtune. You can download it, and then you can take it to a local install of Vtune here. And you can take a peek at it. Is this on my screen? Let me move that out of the way. So you can open your result, and you can see that we did a Vtune on DG1, and you can open the Vtune data. And you can basically play back your run and see what's going on. So you can see, hey, I'm on this platform, so I executed a 2048-16 thing. I actually did use IrisXE Max. You can see your bandwidth, your GPU bandwidth, your write bandwidth, your L3. But really, and this is using the new GPU Media Hotspot preview. So you can also go over here to graphics, and one of the cool things to look at is this memory hierarchy diagram. And this kind of gives you an idea of how your algorithm's working across the entire run of collections. So you can see like your GTI here is 15 gigabits, and you're not really maxing that out, which is a good thing. You can see that your EUs are active at 96%, not stalled. Your occupancy is 99.9%, which is fantastic. It's exactly what you want. And so this is looking like a pretty good run. And then you can come down here, and I know this is tiny. I'm sorry, I can't zoom this interface. But you want to see, you can kind of come down here and see, okay, what's the most active kernel? And we would expect it to be kernel. And we can see that it's running, a 16 by 16. It took 148 seconds. It's packing, it's vectorizing with SIMD32. You can see the URA, and we can see the various things that's happening here. You can also take a look at the platform, and you can zoom in. You can see that you've got this setup data here. What's going on in setup, and that's taking almost 7 seconds is looking like setup, and then finally you're on execution time. So and you can see what's happening, again with your things there. And if you flip back here, and you look at your HPC performance characteristics, you can see that you're doing a really good job of offloading your algorithm, because you're basically not using any CPUs whatsoever. It's only 7.6%, which is what you want, right? Because you chose to run the accelerator. So this is actually a good thing, because that means that your CPUs are available to do other things that might be interesting. Whereas you can see, hey, my GPU is used at 95.3%, which was our intent. So that's just kind of a very high level, quick view of Vtune, and we can do this similar thing with our 8153. This is the exact same. Is it going to blow up? Well, I didn't have that collection ready. Oh, okay, so that one's not going to open for me. You can, in our class, we show you how to tune for hardware analysis on the Xeons and take a little closer look. But that's kind of one of the really cool things you can do with the Project Navigator and Vtune, so that you can take a peek at a more in-depth level and see what's going on with your acceleration. And I would really encourage everyone to go take a peek at Vtune and be able to play it back, because it's a lot nicer than, where we're just basically generating that very first page. You can't actually see what's going on, how the compiler optimized it, if it's using AVX 512 or 256, or is a platform really loading, and how much overhead is set up. So like on some of these smaller arrays, where I was showing you that green graph of, oops, wrong one. Must have closed it. Anyways, where I was showing you that green graph, you can start to see how much of the setup is the issue. So overhead. And with that, thanks for listening. We hope